I also want to give credit to my colleagues from University of Georgia, Tim Stevens and Devin Fitzpatrick. Brian Bledsoe is our major professor, and he wasn't able to make it. So today I want to start by talking about a few stream stability fundamentals. I'm going to give you, should I go closer? 3 tools, compound channel geometry, channel section comparison, and a flow duration curve to help you with this. And then there'll be time for questions at the end, but the first one will probably be, this is complicated. Is this really necessary? So I'll tackle that one. So I'm going to start with the bottom line. This is a quote I got from Dan Mecklenburg just yesterday. It's not up here. I didn't have time to put a new slide in for it, but he says, channels do 2 things. They convey water and they convey sediment. Bridges and culverts are designed to do one thing, which is convey water. So this is the problem that we're trying to solve. And these are the symptoms of the problem. So when I think about stream instability, one of the things that comes to mind is vertical instability. So we have degradation, incision, where we're cutting down. We have aggradation. So on the left-hand side, we have a multi-cell culvert. The opening was too small or maybe too steep. So you had erosion that led to vertical instability with downcutting and undermining risk. So it's threatening the integrity of the structure and your roadway. On the right-hand side, you have aggradation. You have a stream crossing with inadequate sediment transport capacity and a loss of channel capacity and waterway opening. So now you have a risk of increased flooding and roadway overtopping. In addition to vertical instability, I think about horizontal instability. And I divide lateral instability into 2 categories. The bad kind is on the left-hand side. So these would be plan form changes, for example. If you have a braided channel, switching to single thread channel, or vice versa. These could be dimension changes, where you have your cross-section geometry is getting wider or getting narrower. Over on the right-hand side, we have lateral channel migration. So this is when you have a naturally meandering channel, and it naturally shifts over time. The difference is you have erosion on the outside of your meander bend, but this is balanced by deposition to the point bar on the inside. We would call this dynamic equilibrium. So this is a natural process. It's not a bad thing, but you do run into problems if you decide to put a bridge or a culvert at one of these kinds of channels. So this is really not a sediment transport problem as much as it is a flow direction problem. And John Witter from OSU, after the break, is going to be giving a presentation. He'll talk a little bit about flow redirection with veins. So stay tuned for that one. But back on the bad kind, the left-hand side. So as you're thinking about vertical versus horizontal instability, if you think about your bed material versus your bank material, if you have really strong bed material compared to your banks are weaker, you're more likely to see lateral instability. On the other hand, if you have strong, cohesive banks and relatively weaker bed material, you're more likely to see vertical problems. In both cases of vertical or lateral instability, one of the things we want to think about is stream power. So let me explain. So many of you probably already know that streams have power. It's actually measured in watts, just like a light bulb. And it's defined as the rate at which stream work is done. So going back to what Dan Mecklenburg told us, stream channels do 2 things. They transport water and they transport sediment. As hydraulic engineers, we've been good about transporting water, but I'm hoping to help us do a little bit better job of transporting sediment. So here's the equation for stream power. Total stream power is a capital omega on the left side. On the right side, that's gamma. Scary, it's just the unit weight of water. It's a constant, 62.4 cubic pounds per cubic feet. You have Q, that's your water discharge. You have slope. So more water discharge, more slope, more stream power. Specific stream power is when you take the total stream power and you divide it by the stream width. So that's the little omega. And another way that you can think about this is to take the product of the shear stress and velocity. So you're probably more comfortable with shear stress and velocity, but here's this thing called stream power. To think about the difference between total stream power and unit stream power, a good example is to think about the Mississippi River versus a mountain stream. So the Mississippi River has got a lot of sediment in the form of sand. It has a huge amount of flow, discharge, not a lot of slope, but overall it has a really high total stream power. The Mississippi River, though, it's transporting sand. It's not carrying cobbles and boulders. A mountain stream, it doesn't have a lot of discharge, but it's able to carry, the cobbles and the boulders. So if you take the total power of the Mississippi River and you divide it by its really wide width, you end up actually with a pretty small specific stream power or unit stream power. So in this case, it has less stream power than the mountain stream, which can move more and move larger materials. Okay, so here's your first tool. This is compound channel geometry. I stole this from the Ohio DOT Drainage Manual. What you see here, you see a little bankful culvert, and you see, so you have a bankful channel going through that culvert, and you have a floodplain. So those are your two stages. The compound channel is the bankful and the floodplain. I'm not focusing on the culvert so much right now, just the fact that we have a two-stage channel here. So compound channel geometry, the first thing that should come to mind is a bankful, sometimes also called a channel within a channel, or a two-stage channel. Just a hands up, how many people have used bankful or are familiar with bankful already? Great, so glad. Okay, so review. This typically accommodates the 1 to 2 year discharge. Roadway hydraulic engineers were used to designing things for 10-year, 25-year, so we need to sort of wrap our heads around dealing with the 1 and 2 year, because it matters. Within the bankful, you might actually find another level of compound channel. It would be a low flow channel. This would be maybe a base flow channel. It's called a pilot channel. And my favorite term for this is the inner berm. So when you have compound channel, you've got two things. You've got floodplain connectivity, and this is critical especially for the high flows. So you want to put the water up on the floodplain. It brings down the stream power inside your channel. So it reduces your velocity and your shear stress. For low flows, this is critical that you account for sediment transport for the more frequent events. So that now we're in the 1 and 2 year or even more frequent events. So that's critical. So bankful is something that is a tool for you, and actually John Witter is going to talk about that a little bit too, I believe. So this is an example problem. So I worked at EMH&T for almost 4.5 years before I started my Ph.D. program. Miles Hebert spoke yesterday. He was actually my boss. He did the Cannon Drive OSU levee. So this is a little project, and this is a stream channel. It's a little channel. Drainage area is less than a square mile, but we had a problem. So here, the highlight shows you the existing channel. It has cut down over time. So there's been urbanization in the watershed, more flow. So we had vertical incision. And then it has reached the point also where now it's beginning to go side to side. So all sorts of instability. Our solution here was to use a compound channel. So we created a compound channel by excavating out a floodplain. So just excavating, we didn't muck about in the middle of the channel. So what this does is this new floodplain connectivity reduces the channel velocity and the shear stress for the larger storm events. I will caution you that you want to do this when you have dry conditions, because this is being constructed now, and I talked to Miles, and he says it is a muddy mess. So there's an issue there, but it's a solution for you. So this is a way to think about preventing aggradation. This is another project I worked on with EMH&T, and this was constructed last year. We were realigning a stream, and we excavated out a really large 100-year floodplain, so this can carry a lot of flow. But within that floodplain, we also excavated out a smaller meandering bankful channel. And then within our bankful channel, this was my favorite part of this project, we actually put in a little inner berm. So this little inner berm and this bankful channel, they make sure that for the most frequent flows, the flow stays narrow enough and deep enough to transport sediment so we don't deal with aggradation. Okay, so this is a sediment transport quiz. I'm not sure how many people have designed a bridge or a culvert to pass water. I see your hands, loud and proud. Yes, great. How many people have designed a bridge or a culvert to pass sediment? Okay, so that's good. So some of you this might be a relevant quiz for you, so we'll go ahead and go through it. So number 1, sediment data is hard to obtain. The necessary field work is difficult, time-consuming, and generally prohibitively expensive. We got a little taste of this from Brinton's presentation. Who would say that's a true statement? Oh, nobody wants to raise their hand. False statement? How about partly true? I don't know. That's a legitimate response. I don't know. Okay, so I would say this is a partly true statement. So it's true, you need special field conditions and special equipment in order to measure your velocity, your discharge, and your sediment loads to actually know how much sediment is coming to you. But on the other hand, it's actually really easy to perform a pebble count to measure material size, which is used for sediment transport calculations. So the second question is, empirical sediment transport equations can be off by orders of magnitude. Okay, I won't make you raise your hands. Just think about it. Okay, sadly, I think this one is true, and it can be difficult to accurately predict absolute values. So Britton talked about sensitivity analysis as a way to try and deal with that problem. All right, so number 3, this is logical conclusion from 1 and 2. Therefore, sediment transport calculations are impractical and pointless. So you know the answer is going to be false because I'm up here. So what I would say here is a relative comparison of 2 channel sections or scenarios can be relevant and useful. So this is tool number 2. This is channel section comparison. What you see here is a simplified channel section. Some things I'd like to point out to you are the geometry. We have the bottom width, the bank height, the side slopes, the floodplain angle. You also see roughness on the banks and the floodplain. When you're doing this, you're going to need to know your Manning's values for those 2 elements. You also see some sediment in here, maybe some cobbles is what those are. You're going to need a grain size distribution if you're thinking about sediment transport. And the one thing you don't see here, but it's quite important, is the longitudinal slope. So when we're doing channel section comparison, we need this information for 2 sections. Okay, NCHRP project 24-40. This was design hydrology for stream restoration and channel stability at stream crossings. And actually, it's one of the publications that Britton put up there. There was actually a webinar on this past spring. I'm curious, did anybody here participate in that webinar? Okay. So the folks on the right are the ones who presented there. Brian Bledsoe, University of Georgia. Dan Baker, Colorado State University. Those 2 guys are authors of the reports. There was also Bob Hawley from Sustainable Streams and Casey Kramer from Northwest Hydraulic Consultants. So what this project had, we have a research report 853, which you can get online from TRB. There's also a more comprehensive contractor's final report. Some of the things that came out of this project were a decision tree, evaluation of stream response potential, a rapid geomorphic field assessment, and a capacity supply ratio spreadsheet tool. So this capacity supply ratio, this is the channel section comparison. And what you are comparing is the sediment transport capacity of your design reach and your supply reach. So you have a sediment transport equation, which might not be that great all on its own, but if you do it for your design reach and your supply reach and you compare them, now that's useful. So they're both off by orders of magnitude, but relatively, we're actually really close in the ballpark. So when you are designing a bridge or a culvert, you would like to have a target ratio close to 1, meaning that your design reach has the capacity to transport the amount of sediment coming to you. This is actually not a brand new idea. There was a U.S. Army Corps publication back in 2006 by Soar and Thorne talking about CSR. There are other possible channel comparisons that you could do. You could do a pre-project and a post-project analysis at the same section. So if you add a bankful bench to see what the effect would be. You can do this if you have a design reach and a reference reach, if you're using that natural channel design methodology for stream restoration, for example. If anybody's familiar with the Rivermorph software, the PowerSed module inside of that, that's how it's working. It's using a channel comparison between 2 sections. So this is the token slide where you can't read it. So I'll read it for you. This is the capacity supply ratio spreadsheet tool. These are the inputs on the left-hand side. You're going to have inputs for your supply reach and your design reach. You'll have a bank height, the bank angle, your bank roughness, your right and left bank roughness, your floodplain angle, your floodplain roughness. So you'll need that for both your supply and design. For your supply reach, you're going to need your grain size distribution. You will also need your bottom width and your slope. For the design reach, you do not actually enter a bottom width and a slope. What you do is you enter a range of bottom widths you'd like to consider, and it will use the grain distribution from the supply reach, and it will actually give you a range of stable solutions. So in this regard, it's similar to the HEC-RAS stable channel design tool that uses the Copeland method, if you're familiar with that. So in the middle here, you see the results. You have on the x-axis your bottom width, and on the y-axis your slope. And you can see as the bottom width increases, you actually have to increase your slope to account for the fact that you're so wide. Tool number 3 is the flow duration curve. So this is an example of a flow duration curve. All the gray lines represent different years, and the red line is the overall composite. So this came from USGS gauge station at Licking River near Newark, Ohio. Okay, so to explain why this might be important, a single flow would be an example, a design year. So your Q10 or your Q25 that you've been using, your flood check, your Q100 or your Q50. Bankful discharge is another example of a single flow. Effective discharge, half-load discharge, those are similar to bankful. And then, like I mentioned, the HEC-RAS stable channel design, this is also based on a single flow. On the other hand, you have a flow duration curve. This is the full spectrum of flows. We're not talking annual maximums, we're talking daily, hourly, and even if you have it, the 15-minute interval. So everything you can give me from the USGS gauge station. You're talking about the percent of time that flow is met or exceeded. So if you see Q15, that means it's exceeded 15% of the time, or Q75. Sometimes this is expressed opposite. In other words, it's in terms of non-exceedance. So just be careful which one you're talking about. So this is based on stream gauge data, which is a problem because most of our stuff is ungauged. But there's a solution. There are regional flow duration curves that you can create, normalized based on your 2-year flow or your drainage area. So we have a solution. The flow duration curve is actually used to compute the effective discharge and the half-load discharge. So let's look at that for a minute. So on this graph, on the bottom axis, we have water discharge Q. The blue line is your flow frequency. So you can see there's a few small flows, there's quite a lot of mediumly low flows, and then it sort of tapers off as you get to the really, really big flows. The green line is your sediment transport rating curve. So in general, you see as the water discharge increases, your ability to transport sediment increases, both in magnitude and quantity. You might notice this green curve doesn't start all the way at 0. This would be an example of a gravel bed or cobble bed stream where it actually takes a pretty high flow event to even start the material moving. If you had a sand bed stream, for example, this curve might come all the way back down to 0 because you've got material moving even at really low flows. The red line is the product of the blue and the green. So you multiply the flow frequency by the sediment transport rating curve, and you get this, sediment transport rate. The effective discharge is the peak value up at the top there. This curve you can see is a little bit skewed. So if you were to cut it in half and equal weight, this is the half load discharge. That's just a little bit off to the left. That's your QS50. Both of these are in the range of bankful. We're talking about your 1 to 2 year kind of flows here. Okay, so if you only remember one thing about flow duration curves, I want you to remember that you can have a regional flow duration curve for ungauged sites. If you work for an Office of Hydraulic Engineering, I would say that developing these flow duration curves will be comparable to providing your IDF rainfall curves for designers. I would not expect your typical roadway designer to come up with these. I would expect you to give them the tools, and then they could apply them. To create a flow duration curve, you can use ERAMS. This is a free web-based tool. It's from Colorado State. Anyone can use it. And it's not actually that hard, but I will say you need to give some thought as to which gauges you are including for your curve. I would strongly urge you to consider collaboration with USGS or another research institution if you're putting those together. Some possible variables you want to consider would be your rainfall regions, urban versus rural, and flashiness of your stream. And I would refer you to the appendices of the NCHRP 2440 Contractor's Final Report. It has step-by-step instructions for walking you through what you need to do to create a regional flow duration curve. But that is the Contractor's Final Report, not the shorter version, the A53. So this here is a regional flow duration curve I made, and it only took me a couple hours. I used those directions. This is based on some streams in Ohio, and it is normalized by drainage area. So theoretically, using these streams, I could have this overall curve, and if I knew a drainage area of some other stream, I could plug it in and it would give me this flow duration curve. So not that hard. Okay, those were the tools, the compound channel geometry, channel section comparison, flow duration curve. Okay, so now I have the question, is all of this really necessary? Yes, it's complicated. This is a question the authors of NCHRP 2440 were trying to address. When do we actually need to worry about this? The answer is it depends on the stream. And your level of effort should be related to the level of risk in your stream. So they have this phrase they call stream response potential. So if you have a stream that has fine gravel or sand on the bed, that has higher stream response potential. If you have a stream hydrology where it's flashy, that also has a higher stream response potential. This chart that you see on the right-hand side, this is not actually in the publication, but this was developed by Dan Baker, who was one of the authors of the publication. What you see is if you have a coarse bed stream and non-flashy flows, great. It's low risk. You get your choice. You can use a single design discharge for this. You don't have to go through all of the CSR ratio and all of the flow duration curve. So here are your choices: Q bank full, Q effective, or QS50. I want you to notice that Q10 and Q25 are not on this list. So if you have a fine bed stream, fine gravel or sand, and it's flashy, I really hope you've been paying attention, because that is a very high risk stream, and no single flow is considered appropriate there. You need to worry about all of this. If you have something in between, it's either non-flashy or it's coarse bed, but there's something else. You have this QS50, and it's just one number in there, but remember, you have to use the flow duration curve to come up with that QS50, so this is a little bit more complex. So this is risk based on just the stream. I would urge you to consider risk based on transportation and structures. So for example, if you have a scour critical structure, that would lead you to spend some more time thinking about sediment transport. Traffic volume, if you're dealing with an interstate or a freeway, you probably want to spend more time looking at sediment transport. If you're in a FEMA floodplain, I would not want to mess up a FEMA floodplain by accidentally messing up the capacity and causing aggradation in my floodplain. So before I take questions, I'd just like to say, if you missed the webinar, one of the things we're doing right now is developing short course materials. And if you're interested in learning more about that, please look me up afterwards, and I'll take questions. Yes?
So you talked about gravel, bedrock. What about if you have finer, like sort of clay?
Right, so you have finer materials, fine gravel, sand, clay. That would be high-risk material.
Even though it has a cohesion, doesn't sand has to be more cohesionless? That doesn't impact that?
So when you have bank cohesion, for sure, this clay is good in the banks. I'm not going to say yes or no on the stream bed, but it's small particles, so I would say it is risky. Okay, thank you for your time.